Hello everyone, my name is Dr. K.C. Apparao, working as an associate professor in mechanical engineering department. Today I would like to explain on natural convection. In previous classes we saw uh, the significance or importance of the forced convection, what are the different formulas are included in forced convection. Also, one or two numericals already we discussed on the forced convection also. Now we'll see what is the phenomena of natural convection, what are the different parameters which are included in natural convection also. We'll see. We know that natural convection, so this is the free convection because we know that convection is completely associated with the bulk movement of the particles. So without movement of the particle, there is no convection process. So for the movement of the particles, there are two ways. One is by naturally or by the effect of buoyancy or by using some external agent like some fans, uh, some some external agent. Okay. So, but in some cases, by the effect of buoyancy, by the difference of the density, particles move from bottom to top. You know that one. So, when if you heat it at bottom, then the particles which are very near to the surface, those particles will be heated. That heated particles have less density. Less dense particles moves into upward direction. Heavy dense particles moves into downward direction. So in this way, heat is transferred from bottom to top. So here, particle movements occurs by the effect of the buoyancy. So this is nothing but natural convection. We already discussed in previous class also. Okay. So in natural convection, here also we'll see two types of flows. One is the laminar flow and another one is the turbulent flow, similar to forced convection. So to identify the type of flow, here we will use the Grashof number. Okay. So in forced convection, we use the Reynolds number to identify the flow. Okay. But here in natural convection, we will use Grashof number to identify the type of flow. Okay. So this is the velocity profile. This is the temperature profile in natural convection. So this is the velocity profile. So velocity initially low, then it is increases, it reaches maximum, then gradually decreases. So temperature, because surface temperature is greater than the Tf, so here temperature is very high, it gradually reaches to bottom. So this is the bulk temperature. So this one is the temperature profile, this is the velocity profile. So this one is the boundary layer, like this one you can understand. So x is in vertical direction, you can take x or y. Okay. So this is the just like boundary layer diagram and velocity profiles and temperature profiles. So same situations we assign forced convection also. Now this one here, if you take, this is the just like one particle, warm fluid. The friction forces act in downward direction, but buoyancy forces, which is related to density. Okay, less density particles moves in the upward direction by the effect of buoyancy, but friction force opposes from the top to bottom. So this one is the hard surface, this one is the cold surface. So this phenomena is related to natural convection process. Okay. You know that too, the Grashof number. Here, natural convection, we have to find out the Nusselt formula, because you know that Nusselt is equal to HL by K or HX by K. H is the heat transfer coefficient, you have to find out that one. K is the thermal conductivity. L is the given length, or you can length of the plate. So complete length you can take. If it is circular pipe, you can take diameter HD. So you have to find out the Nusselt formula in forced convection, in natural convection also. If you know the Nusselt, then you can find out the H value. Automatically, you can find out the rate of heat transfer H into delta T. Okay. So, but in natural convection, Nusselt is the function of mm, Grashof number into Prandtl number. So, but in forced convection, Nusselt is the function of Reynolds number and the Prandtl number. In place of Reynolds, we here will see Grashof number. So we'll see what is Grashof number. Grashof number is nothing but buoyancy force by viscous force. Okay. So it is represented with GR. This is the final formula. G beta delta T LC cube characteristic length cube by kinematic viscosity square. Okay. G is the acceleration due to gravity. Beta is the coefficient of volume. Beta is nothing but 1 by T mean. You know that T mean is equal to temperature, average of temperatures. So T S plus T F by 2. You know this one. Okay. Delta T is the temperature difference. You know this one. LC is the characteristic length. It is depend upon the geometry, which type of geometry you are using to flow the uh, fluid, to move the fluid. Okay. So by using all the parameters, you can find out the uh, Grashof number. And Prandtl number you can take directly from the data book. Otherwise, you have to find out to mu Cp by K by using these formulas. You can find out Prandtl number. So the product of Grashof and Prandtl number. So GR and PR, the value of GR PR, it decides the type of flow. What type of flow? Either laminar or turbulent. Here we'll see just like empirical relations for the free convection. So in case of free convection, heat transfer coefficient or Nusselt is expressed as the, you know, the formula HL by K. So HL by K is the function of Grashof number and Prandtl number. Okay. So Nusselt Nu is nothing but Nusselt number. GR is the Grashof number. PR is the Prandtl number. Okay. Here some formulas are there. So if you take vertical plate, so the flows. If the fluid is flows on a vertical plate, then you can take this type of formulas. And if the fluid is flows in cylinders also, you can take these formulas, Nusselt formulas, based upon the Grashof product GR into PR value. Okay. If the GRPR is less than 10 to the power of 5, so you can take this formula 0.53 GRPR whole to the power of 100. Okay. If the GRPR is less than 10 to the power of 8, so in between 10 to the power of 5 to 10 to the power of 8, so 0.56 GRPR whole to the power of 100. If the Grashof product GRPR value is in between 10 to the power of 8 to 10 to the power of 12, then you can choose this form. Okay. So based upon the product of GRPR, you can identify the Nusselt form. So L is the characteristic length and it is the height of the plate or cylinder, and H is the average heat transfer. It is the height of the plate means, um, so when the plate is in vertical position, you know this one. Okay. So for the horizontal cylinders, these are the formulas you can take. So if the Prandtl GRPR value is equal to 1 by 10 to 10 to the power of 4 in between this one, then you can choose this formula. In between 10 to the power of 4 to 10 to the power of 9, you can choose this formula. 10 to the power of 9 to 10 to the power of 12, you can choose this formula. So these are the if the geometry in horizontal cylinders. Okay. In case of vertical cylinders, previous formulas you can prefer. So for the horizontal positioning cylinders, you can take these formulas. Okay. L is the characteristic length in this case. So it is the diameter of the cylinder that is equal to. Okay. So you can use these formulas. Vertical cylinder LC is equal to L, that is nothing but height you can take. Horizontal cylinder LC is equal to diameter. For the horizontal plate, so area by perimeter, by using this formula, okay, you can find out the LC. So identifying or finding of LC, characteristic length, is very important here. Okay. So because gross of number is depend upon the LC cube also, directly proportional. So this product of gross of number or Prandtl number, nothing but Rayleigh number. You can take like this one, RA. RA is nothing but GR, PR. Otherwise, you can tell, we can tell GR, PR also. If the RA, if the RA or GR, PR product is less than 10 to the power of 9, that shows the laminar flow. You have to remember this. So, uh, flow identification, it is depend upon GR and PR in natural convection. So flow identification is depend upon Reynolds number in forced convection. You know this one. So if greater than 10 to the power of 9 GRPR value, that shows the turbulent flow. Okay. So here we'll see one numerical based upon this one. A horizontal pipe. So that is the diameter of the pipe has been given 10 to that is the 30.5 centimeter diameter, is maintained at a temperature. So temperature of pipe temperature is equal to 250 degrees Celsius. Okay. So horizontal pipe. So pipe is positioned in a horizontal. Diameter has been given. Length also given. Okay. So the temperature of the pipe. So that one is Ts is equal to 250 degrees Celsius. Okay. Next, ambient temperature, it means Tf is equal to 20 degrees Celsius. Calculate the convection heat loss per meter length of the pipe. Meter length means L is equal to 1 meter. L is equal to 1 meter. This one. If you know the Ts and Tf, you can find out the um, properties. Properties of fluid. What type of fluid here? So just atmospheric air, dry air. So that is the fluid. You can take the properties of dry air by the help of T mean. So T mean is equal to Ts plus Tf by 2. That is the 250 plus 20. So 270 by 2. Okay. So by using this temperature 135 degrees Celsius, at 135 degrees Celsius with respect to that dry air, you can take the properties. Okay. By using, so here already the properties of the fluid also given, you can use this one. Thermal conductivity of the fluid is equal to 0.0234 watt per meter degree Celsius. Prandtl value, that is 0.68. So kinematic viscosity also given. You can use this one. So this is the just like pipe. So surrounding. So this one is the free convection. Convection takes from less density particle, heavy density particles moves downward direction, less density particle moves into upward direction. Okay. So it means here characteristic length is the diameter of the pipe. So this one, diameter of the pipe, you can take like this. So because this is a natural convection, movement of the particles from bottom to top. So it moves up to diameter distance. So you know that formula of gross of number. Gross of number is equal to G beta into delta T into L cube by kinematic viscosity square. Okay. G, gross of number G is equal to G beta into delta T LC cube by mu square, kinematic viscosity. This value given. LC also diameter, you know this one. Delta T temperature difference, you know this one. Beta is equal to 1 by T mean plus 273. You have to convert into kelvins. And G is the acceleration due to gravity, 9.81. You know all the values. If you substitute those values, you can find out gross up number. So this is the G value. Next to temperature difference. Next to beta value. Beta value. This is the temperature difference 230, and the LC. Um, so cube characteristic length 0.305. So by 408 means, so that is the T mean value in kelvins into kinematics viscosity square. So we got this value 2.27 into 10 to the power of 8. So this is less than 10 to the power of 9. It shows this is the laminar flow. So then you can take the formulas which are related to laminar flow. You know that general formula. This is the function of gross up number and the Prandtl number for the Nusselt value. So Nusselt is equal to C into GRPR into all to the power of n. Okay. So Nusselt is equal to, you can take, this is the 0.125 into 2.227 into 10 to the power of 8. So this is the gross up value to the power of 1 by 3 means 333, 0.333. So by using the page number, according to page number 146 3.1 session, you can section, you can take the formula. So if you refer this to Kodan data book, you can understand this one also. So then the Nusselt value is equal to 66.4. Okay, Nusselt value is equal to 66.4. So if you know the Nusselt value, then you know that formula. So H LC by K. LC is nothing but diameter. You know this one. Then K is the thermal conductivity already given in numerical. Then you can find out the H value. So because you know Nusselt value, so if you substitute all the values, then you can find out H. H is nothing but 5.11 watt per meter square Kelvin. Okay. So if you know the H, then you can find out the Q value. So Q is equal to area HA into delta T. Delta T is the temperature difference, Ts minus Tf, and A is the area. Okay. So 2 pi L or perimeter into length. Okay. Otherwise 2 pi into length. Length is equal to 1. You can take. Okay. So then if you substitute all the values, then you can find out the Q value. Q is equal to 1127.8 watts. So in this way, just we can solve the different numericals. One numerical also has been given here. You can see here. Vertical pipe, so 10 centimeter OD at surface temperature of 100 degrees Celsius in a room temperature. So here pipe temperature Ts is equal to 100 degrees Celsius, and ambient temperature Tf is equal to 20 degrees Celsius. Diameter D is equal to 10 centimeter. So all the data is given. The pipe is in 3 meter long. L of the pipe 3 meter long. So what is the rate of heat loss? So we have to find out Q value. And the properties also given here. Thermal conductivity of the fluid, the air thermal conductivity. Next to Prandtl value of the thermal conductivity also given. Kinematic viscosity of the fluid. So air has been given. You can find out the remaining parameters. It means first of all you have to find out the gross of value. Then here Prandtl also given. Then you have to find the product of gross up on the Prandtl value. Then you have to identify the which type of flow. Then by using the gross up value, product of GRPR, and the type of flow, laminar flow or turbulent flow, then you can choose the Nusselt formula. Nusselt is equal to C of GRPR to the power of n. Okay. Okay. So C and N values depend upon the value of GRPR and the type of flow. Okay. Here we'll see diagrams. This is the uh, vertical pipe has been given. So here the particle moves from top to bottom. So characteristic length means height of the pipe here you can take. So here LC is equal to length of the pipe. construct this one. So T mean is nothing but T S plus TF by TF by 2 and 100 plus 20, 20 120 by 2 60 degrees Celsius. So by using this property temperature you can find out the properties, but properties of the fluid already given. Okay, so by using this one you can find out the beta 1 by T mean plus 273 in Kelvin. Okay, so that is 1 by 33 triple 3. Then you can find out the Grashof number. Grashof number formula, you know this one. So Grashof number formula is equal to G beta delta T LC cube by nu square. G beta, you know this one. 1 by T mean 1 by triple 3. 9.81 is the G value. Delta T is the 100 minus 20, 80. LC is the length of the pipe, that is 3 meters. Kinematic viscosity, so the value of kinematic viscosity of air also given. If you substitute the values, you can find out the GR value. Then you have to find out the GR and PR value. So this is greater than 10 to the power of 9. So this is greater than 10 to the power of 9 means this is the turbulent flow. Turbulent flow. You can identify this one. So by range of Grashof and Prandtl, you can take the Nusselt formulas. Okay. So Nusselt formula is here. So Nusselt is for the full length 0.1 into GRPR whole to the power of 1 by 3 means 0.333. So you can refer the page number 144 according to Kodan Raman data book. Then you can understand this one. Okay. So then you know the formula Nusselt is equal to just because of this positioning 5 by 4 Nusselt of full length is equal to, this is the value. Then if you find the Nusselt value, that Nusselt value is equal to HL by K. HL by K. By using this one, you can identify, you can find out the H value. If you know the H value, automatically you can find out the rate of heat transfer. Rate of heat transfer is equal to HA into delta T. Okay. So one more numerical, you can refer this one. Just I am leaving this one. These are the one more numerical. You can refer this one. Okay. So these are the different test books you can refer to solve different numericals which are based on the natural convection. Thank you for this listening. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.